In this lecture, we're going to see a very badly behaved example of injective immersion. Indeed, our immersion is not going to be surjective, but its image is going to be a dense subset of the target space. Let's see an example of the kind of pathologies or very bad pathologies that we can have. And the example is going to be the torus T2. Let's going to consider in the plane the equivalence relation that actually relates 2 points, x1, y1 and x2, y2, if the difference of the first coordinates is an integer number and the difference of the second coordinates is also an integer number. And let's say that T2 is the set of equivalence classes. We have a quotient map, natural quotient map, that sends a point of R2 in its equivalence class. And indeed, we can use this map to give a topology in the torus. This topology is the one in which a subset of the torus is open if the preimage is open. That's what's called the quotient topology. The local charts, we can try to give a structure of differentiable manifold of our torus that will be natural. And what we want to use as local charts are the simplest possible maps. In our case, the local inverses of pi. You have to consider that we are working in the plane R2, and when we have a point, the points that belong to the same equivalence class are the ones that are obtained by adding to our point an integer vector, a vector whose coordinates are integer numbers. So we have something like this, more or less. Those are the representatives of the same class. And all these representatives are actually sent to the same point because they are all representatives of the same class. So a point over here. What happens is that if we consider a small neighborhood, then in that neighborhood you don't have points that represent different classes, because if the neighborhood is small and the difference of the coordinates is an integer number, it has to be 0. So we're going to have here a map pi, which is the restriction of our quotient map, which is going to be a bijection, just locally. And here we're going to have another bijection. And we can consider the local charts to be the inverses of these local bijections. And then what is going to be the coordinate changes? The coordinate changes are actually maps that send points to points that are representatives of the same classes. So these coordinate changes are going to be translation and the translation vectors are going to be vectors whose coordinates are both integer numbers. So we are in a situation in which we can actually give a structure of manifold in which the coordinate changes are actually translations. So in particular, they are real analytic. So the torus has a structure of real analytic differentiable manifold. You can do this also if you just consider R. We can actually consider R, and in R defining an equivalence relation that could be x1 is in the same class as x2 if x1 minus x2 belongs to C. And what we're going to do is call in R over C to the set of equivalence classes, and by an analogous argument, what we have is that such a set is a real analytic manifold of dimension 1, whereas the torus is a real analytic manifold of dimension 2. So we define the torus T2. We can also use this notation, okay, as a quotient of R2 and C2, as a quotient of abelian groups. And what we are going to point out right now is our torus is actually a compact manifold. And the reason is that the torus is actually the image by pi of the square closed interval 0, 1 by itself. Because if you have a class, any class, this class has a representative which is a vector with both coordinates between 0 and 1. You just have to add integer numbers to both coordinates so that both of them are between 0 and 1. Since the square is a compact set and pi is a continuous map, the image of a compact set by a continuous map is a compact set, and so the torus is actually a compact real analytic manifold. If you do the same construction with R, what you get is also a compact real analytic manifold. But first, let's try to visualize the torus. We have the square. We can actually restrict ourselves to the square because the square has at least one representative for every equivalence class. But in the square, there are actually classes that are representative more than one time. For instance, you can have here a point 0x and here a point 1x, and these 2 points are identified. And the same thing happens with points that are in the left and right sides. The same way happens if you consider the top and bottom sides. For instance, this point over here could be the x1 and this one the x0, and they are also identified. So what we have to do in order to obtain our abstract manifold is identifying top to bottom, gluing top to bottom. In that way, we are going to obtain a cylinder. And in this cylinder, this left side is transformed into this circle because in this left side, we are identifying the top point and the bottom point. Analogously, the right side is transformed into this right circle because, again, the top point is identified with the bottom point. But now we have to realize that we have to identify also the left and right sides, so the left and right circles. And when we do this, we get the torus. That's the reason we are calling this the torus T2. If we do the same construction with R, I mean, we consider this space, the space of equivalence classes of real numbers, in which we are identifying x1 and x2 if the difference is an integer number. In an analogous way, we can see that this is a compact real analytic manifold, and what we have to consider here is the interval 0, 1, because every class has at least one representative in this closed interval, but in the interval, there are 2 points that have to be identified because they belong to the same class, which are 0 and 1. And when you do this, you get the circle. So if you perform this construction with R2, you get the torus. If you do it with R, you get the circle. If you do it with R3, you get the three-dimensional torus, and so on. Okay? But why are we doing this? Because we want to give an example of very badly behaved immersions. So in order to do this, consider lambda, which is going to be a real number which is not rational. And that's going to be a crucial property in this example. And we consider the map from R to the torus defined in this way. F of t is just the class of t times lambda. This is a differentiable map, okay? And we want to understand the properties of this map. Okay, F is an injective immersion, but it's not a proper map. Some of the properties here are very simple. In particular, it is obvious that it is not proper. Because if you consider the preimage of the whole torus, okay, this is R. The torus is compact and the line is not compact. So F is not a proper map. But it is an injective immersion because the expression of F in local charts is just t times lambda. And the differential of F at any point, since this map is actually linear, is going to be the linear map whose matrix is 1 lambda. And this map is always injective. It has always maximal rank. So we are in a situation in which F is an immersion. Besides that, it is also injective. That's where we're going to use that lambda is an irrational number. Because if you have that 2 points, T and S, have the same image, that implies that the classes of T and T times lambda and the class of S and S times lambda are the same. But this implies that t minus S is an integer number, and also that T times lambda minus S times lambda is also an integer number. If for whatever reason this is different than 0, then you can write lambda as the quotient of two integer numbers, this one and this one, and then lambda could be rational. And that's actually contradicting our hypothesis. So the unique situation in which lambda is if we cannot deduce that it's rational is if t is equal to s. And so in this way, we proved that F is injective. It's an injective immersion, which is not a proper map. Okay, so we have our first property. The second property is that F, the image of F, is a dense subset of the torus. Okay, let's focus on this one. Let's consider the projection from the line to the quotient of R over C. We already know that that's going to be a circle. And what we want actually to see is the following lemma. If we consider the set of classes of the form of lambda times k, the class of lambda times k, where k is an integer number, this is a dense set of the circle. What we want is showing this. Okay, so how do we do this? First of all, you have to realize that exactly the same as it happens for the torus, all these points are different, okay? If the class of k times lambda is the same as the class of k prime times lambda, and k prime are integer numbers, that's going to imply that k equal k prime, because k minus k prime times lambda has to be an integer number, but if k is different than k prime, you can actually write down lambda as a quotient of two integer numbers, and that would prove that lambda is rational, which is actually not the case. So k equal k prime. So if we call this set over here S, what our first argument is actually proving is that S is an infinite set. It's indeed an infinite subset of the quotient. The quotient has a structure indeed of abelian group, because you can actually consider, you can actually sum classes. The class of X plus the class of Y is the class of X plus Y. And it's very, very easy to see that this is well defined and the quotient is an abelian group. So we have that S, let's go back to our proof. S is an infinite subset of this circle. And since the circle is compact, since our manifold is compact, that implies in particular that there is a sequence of different points that converge. So there exists a sequence K sub n in the set of integer numbers such that the limit when n converges to infinity of the class of kn times lambda is some point that, I don't know, let's call, for instance, P. So we have some point P and points here that converge to P. But what we can actually realize is that if n and m, both of them converge to infinity, and we consider the limit of these classes, okay, this is going to be the limit when n goes to infinity of kn times lambda, the class of kn times lambda, minus the limit when m tends to infinity of the class of kn times lambda, that's p minus p, which is the class of 0. Okay, so the neutral element of the group. So in particular, we can suppose by using this trick, by changing the kn's by difference of the different kj's, we can suppose that this p is actually the class of 0. And so that we have a sequence of different elements that go to 0. And that's going to imply that our set, or let's remind that our set was the set of classes of elements of the form k times lambda, where k is an integer number. this set is actually going to be dense. Why is that? Let's do it with a picture. Here we have 0. And we know that there is a sequence of elements that go to this point, that tend to this point here. These points could be points of the form class of k sub n times lambda. If we fix any other point, for instance, between 0 and 1, okay, a point, for instance, let's say here, and we fix an interval, a small interval around that point, we want to show that there is a point of this form in the interval. But that's not very difficult, because if the interval, for instance, has radius epsilon, what we can do is considering a point over here, which is a distance smaller than epsilon from 0, and then adding this point. And this point is going to be going to the right in jumps that are of length smaller than epsilon. So at some point you're going to get in here, and you're going to have a point of this form in this interval. And that happens for every point. So this set is dense, right? That's what we are going to have. So let's remember, let's remind ourselves of what we want to prove. We want to prove that this image is a dense subset of the torus, right? So let's fix for a minute a class inside the torus. And what we want is finding elements in the image of F that are arbitrarily close to this point. So what can we do? We can consider the image of points of the form x0 plus k, where k here is a parameter, but it's an integer parameter. We are varying k in the set of integer numbers. What is the image of x0 plus k? It's going to be the class of x0 plus k and lambda times x0 plus k. But since we can subtract any integer number from any of the coordinates, this is going to be the class of x0 lambda times x0 plus lambda times k. Indeed, it's going to be the class of x0 lambda times x0 plus the class of 0 lambda times k. But what we have to remind now is that the class of lambda k in the second coordinate actually is dense. And when we add lambda x0, it's still going to be a dense set. So because of the lemma we just proved, what we get is that the image of, let's say, x0 plus c has a closure that contains every point, every class of a point of the form x0 and second coordinate can be anything, where y belongs to R. In particular, it's going to contain the class of x0, y0. So this point is also going to be in the closure of the image of F. And so because of that, the image is a dense subset of the torus. Obviously, since the image is a dense subset of the torus, it's not submanifold. We didn't explicitly define what a submanifold is, but the definition of submanifold is local. So what you have to do is just go into local charts as usual, and the definition is going to be the usual one. And since we are not in a situation in which up to a diffeomorphism, our manifold is just going to be aligned. What we want is that in the neighborhood of every point of our manifold, we should have diffeomorphism that actually sends that neighborhood to an open subset of R2 such that the image of our candidate submanifold is aligned. That's not going to happen because a line is not dense in such an open set, so it's not going to happen. So the image of R is not going to be a submanifold of the torus. We have an injective immersion that it is very, very far away from being a submanifold, and in particular, it's very far away because the image is dense. Here we have a picture of what happens, but what's going to happen is that when we follow this picture, okay, this is going to turn around in a way that it is injective, okay? We're not going through the same point twice, but still, it is going to be dense, okay? So immersions can be really bad, at least in this sense of trying to understand if the image is a submanifold. The answer is not even close. So we saw that immersions can behave very badly. In the next lecture, we're going to consider well-behaved immersions, the so-called embeddings. Those are immersions, injective immersions, such that the image is always a submanifold. And indeed, we are going to give a sufficient condition for an injective immersion to be an embedding. Thank you for your attention.